Um, so hi everyone, welcome back. So I believe that today it's the lecture 8 already in the class. And so, okay, let's try to recap where we were and what are we going to try to do today. Okay, so from last lecture, not necessarily like lecture 7, but from last lectures. One of the themes that we described last lectures was that one of the important questions that the deep learning tries to answer is basically how to find or describe good functional spaces. Okay, and here good, I just put it in quotes because what I mean is what I want is to basically have small complexity. It's called gamma f for the functions that we care about, right? For function f that we care about. Okay, so in other words, we want feasible learning. We're going to identify these functions even when the number of samples, n, is much smaller than, let's say, epsilon to the minus t. Okay? And so what we said is that for this goal, kind of the classic functional spaces, let's say sub f, do not basically do not work well Why is that? Because if we want to break the curse of dimensionality, the only way we can do it is to add more and more smoothness to the target function, right? And this is not the sort of smoothness that we typically encounter in these problems, right? We don't have to smooth in every direction, okay? Regularity is too generic. Okay, and then we also described in my last lecture kind of an alternative to this Sobolev space that is this Baron space, right? So the Baron space that, if you remember, was defined as the space of functions f from the input space to, let's say, to the reals, such that f of x can be written as an integral representation of some unit against a measure with the norm of the measure with essentially like a TV norm. So the TV of the measure to be found. Okay, so the Baron space is, and this, remember that this basically the norm of f in this space, if you remember from Baron, that this can be controlled by something that, if you want to relate it to something that you understand, that you touch, that you can a bit more explicit, you can relate it to this quantity that was some kind of a norm of the W times the L1 norm of the Fourier transform. Okay, so that's what we described a few weeks ago. So these are also is a hypothesis. So this space corresponds to shallow learning. Okay, so what I mean by that is that this architecture, so like this space of functions, is the one that is essentially explaining, underpinning everything that we can learn with shallow neural networks. So the question is really, is this space of functions adapted to, to explain and approximate well the functions that we care about in the real world. And so the problem again is that so maybe just to motivate why this might not be the, so there's different ways to answer this question. The first is, okay, we can, you can take a look at what happens in practice, right? So if you look at people trying to, let's say, solve problems in classification, image classification, or protein folding, or things like this, how many of these architectures that work very well in practice are of this form, shallow? In fact, not so many, right? Like these architectures, in a sense, do not, like basically the regularity that is enforced, the regularity in this sense, is not necessarily well adapted to the kind of functions that we care about in the physical world. And in essence, just to get like the intuition here of why there's something that is fundamentally missing in this picture, is that how can we actually understand, at the, like without going too much into the technical level, which functions are invariant, right? So which functions have a Barrow norm that is not too large. So basically, like I'm going to write it like this: morally, functions invariant space are such that f of x is approximately equal to a sum from k equals 1 to k of functions that depend on just projections of the data, right? So like basically think about this as some kind of a, so this is like a k-dimensional, and this is a linear projection. Okay, so basically what it means is that these are functions that what they do, they look at this, like let's say the input is the image, and they decide of, I'm going to project it, right? I'm going to just extract information over a small dimension space, right? So this k here, right? So this k is much smaller than d, right? So k is basically the number, right? The k is replacing d in the sample complexity, right? So everything that was cursed because epsilon to the minus d was very small, sorry, was very large. Now you replace it by epsilon to the minus k, right? So if k is, let's say, constant, right, then you get the good answer. So if you think about like an image, right? That's the input of an image, right? X would be like a picture of someone, whatever. Okay. And so how can you connect, this model of approximation with an image that would look like that, right? So that's what be X. So if you think about what these projections could look like, think that you are taking the image and you're breaking it into little patches. Okay. And so every patch, right? So like if you extract information that is in a patch, you can associate it with one of such projections, right? So UK of X, it would be just like take the image and then just look at what happens in a local patch, right? So this would be one, this would be another one, etc. Okay. And so this kind of model, what it says is that, okay, maybe the information that I need to extract at every patch can be very complicated, right? I need, this function here can be arbitrary, but whatever I do with this information, I'm going to aggregate it with an average, with a sum. So in other words, this model is essentially disregarding the interactions between what happened at different patches. So you see that if there's, the number of patches is proportional to the number of pixels, right? So if you still want to account for everything that could happen, you still need to have like a number of terms here that can grow very large, right? It could even grow exponentially with image. Okay, so this model is really perhaps not totally adapted to the kind of functions that we might want to be learning, right? That we might care about. Okay, so basically local interactions right? So basically, what it means is that here we are kind of we are not able to account. In essence, we cannot extract interactions that basically are long range. All right. So today, we will discuss an alternative based on two, let's say, yeah, on two basically key principles, which are symmetries and, let's say, stability or scale. Okay, so we are going to see, I mean, how from this paradigm and discuss functional spaces that incorporate these notions of symmetry and scale separation. Okay, so that's what we're going to do today. Okay, so far, our input space, right? We have defined it is has been X, which is a high dimensional space. For example, just RD, right, with D very large. But in many applications, right, but in actually most applications, this is an abstraction that is maybe too strong, right? In many applications, the input is not just like a high dimensional vector, it's an image, or like a slice of audio or a protein, right? So these are, of course, you can model them with vectors, but there's another layer of rich structure that we are throwing away. Okay, so structure.
You're back.
Back.
Okay.
All right. Okay. Sorry, there was a problem with my Wi-Fi. Do you still see my screen?
Yes.
Perfect. Okay, there we are. So I can just erase what I was wrong. I thought that my iPad was still connected, so I could only communicate by writing. Okay, so we have more structure, as I was saying, and so basically now we introduce another domain, right? So before we had our high dimensional space. Now we introduce another domain, which is the domain space, right? Like that's the input space, and this is the domain. And so let's do an example, right? So like an example for images, right? When we write our grid of pixels, our domain, right? Is just a domain is like a grid of pixels, right? So like this is a two-dimensional grid of pixels. Okay, and so we have essentially for every one of this pixel, we go to R3, which would be the the RGB colors. Okay, for speech, the domain could be, let's say, time, right? Like just let's say positive time, right? And then X is X of t, right? It's a time series. Like I don't know if you have seen this kind of recordings, right? You get like your input is just a wave sound. Okay, and so in all these examples, the essentially there's one source of structure that these high dimensional inputs have, which is the domain, right? In all these examples, the domains are low dimensional, right? In the case of a grid, it's a domain that lives in 2 dimensions. In the case of a speech, it's a domain that lives in 1 dimension. In the case of a protein, it's a domain that lives in 3 dimensions, right? In all these examples, basically the high dimensionality of the input kind of is hiding an underlying low dimensional structure. Okay. And so if you want to just to visualize exactly what I'm trying to say here, right, is that we have, let's see if I can make this drawing. So we have these, we have three levels of functions, right? So we have, let's call this x. Let's write it like this. Sorry, I can write it here. X, which is the input. Then we have functions that go from x to r. So these are the functions we need to learn. Functions okay, and then we have the domain. Let's call it like the data domain. Signal. What we say is that these x, right, these are just also functions from omega to, let's say, like a low dimensional space. Well, let's say that this R is just for, let's say, grayscale images, right? So we have really these 3 different levels of the hierarchy, if you want, right? We have, the very, very big space, right? This is the space of hypotheses, right? Which is extremely, extremely high dimensional. Then we have the space of signals, which is also high dimensional, right? Which is like the number of degrees of freedom here would correspond to the number of pixels, right? So this is and then we have the other one, which is the domain, right? So basically, very high dimensional, right? F. This is still like high dimensional, and this is low dimensional. Okay, so this is important. I mean, and I'll be using this notation, and that's the notation that we are also using in the book. So just to make clear, okay. And if there's any question, just please let me know. All right. So now the question, of course, is how can we use such a low dimensional structure, right? So like the important question is how can we use such low dimensional structure? Okay, and so for this we are going to now introduce the notion of symmetries, right? Or like discuss symmetries. So what is a symmetry? So symmetries are known transformations of the input x that do not modify the function of interest. Okay, so more formally, right? So for f, a function class, that has functions that go from x to r, symmetry is an invertible transformation. It is an invertible map that goes from x to x, such that for all f in the family and for all input, we have that f of t of x is equal to f of x. Okay, so it's really like you should really just think it of this, like finding transformation directions, right, in which the function I want to learn is very smooth. In that case, the function doesn't even change, right? So if I know in advance the directions in which the function I want to learn is very smooth, it's very natural that I try to use it in my learning, right? Because I don't need to learn any kind of variations, right, and along that direction. Right, but there's a question, of course, is that X now is a very high dimensional space, right? So how can we actually articulate what are the symmetries of the functions we care about, right? So how can we describe symmetries of a space that is very high dimensional? So in a sense, like an issue, right, is that the space of symmetries, right, like the space of possible symmetries in X is huge, right? So X is a very high dimensional space. So imagine like describing matrices, right? Transformations that go from this high dimensional space to itself. Very large. So the whole point, right, is that we are going to use instead, we use the domain to prescribe symmetries. Okay, so instead of using this X, capital X, to think about symmetries, let's use the domain instead to think about symmetries. Okay, so for example, right, so like the question is like think, for example, about a grid, right, like a grid. Let me just for convenience just draw the grid in 1D. Okay, so grid of points. And even a further assumption, right, is that I'm gonna, so a grid is basically a bunch of pixels that are organized into like equispaced in some domain, right? So here would be like a grid in 1D. Okay. And let me also make this simplification. I hope that you're gonna forgive me for it. That I'm gonna just pretend that this pixel is also connected with this pixel, right? So the underlying model, the underlying grid, if you want, is just a ring, right? In that case. So when you see this structure, you might already visualize immediately what are the symmetries of this structure. So what are the ways I can modify this structure so that it stays the same, right? So what are the transformations that I can make to the elements of that structure that leave the structure invariant the same, right? So clearly, here we can define shifts, right? We can decide to move things around, right? So we can, if we just decide that this guy moves here, this guy moves here, this guy moves here, right? These transformations basically leave the domain invariant. Okay, so the structure like this, the notion of neighborhood is preserved if I just move everyone, right, in one direction. So translations are mappings, invertible mappings from the grid to the grid, that you take an element, let's call it I, and you map it to its neighbor, right? And this operation, of course, is taken modulo the size of the grid, right? So that's modulo the size. Okay. And so once I have these transformations, right, and of course, every domain, right, might have different transformations. For example, if I now replace, like this is the discrete, right? It's a discrete grid, right? So here I decided to have a number of pixels that is, I don't know, like 10 or 100, whatever, right? We can play the same game by replacing the same, replacing the discrete grid by maybe just the continuous, let's say the continuous sphere, right? If you think about problems where the input would be just like any signal that is defined over the sphere, the 3D sphere. Or you could think about like a transformation that is, let's say, for time series, where the relevant transformation, right, like the relevant transformation of the domain would be just like a temporal translation of the domain, right? So another example, if the domain is, let's say, R, right? That is the like for time series. Then T is just a mapping that goes from R to R, and it maps T to maybe some T minus T0, right? This is just like a time shift. Okay, and we are going to see also more examples. For example, if, in the case where you want to process some data that is on a graph, there's transformations of the graph that do not change its structure, and these are permutations, right? So you can just take the elements of the graph and just reorder them, right? So the reordering the elements of the graph doesn't change the nature of the graph. The same way that shifting the position of the pixels doesn't change the nature of the grid, right? So this is also like another transformation that follows exactly into the same umbrella. And so once we have transformations of the grid, we can lift them, right? We can upgrade them to symmetries of the signals, right? So how to do that? Okay, so a transformation symmetry, if you want. On omega can be, let's call it, upgraded to a transformation in X, right? Because there's a very natural link between the domain omega and the input space X, right? So because the input domain is just X's that go from the omega to R, right? So how do we make this connection, right? So let's call it by use of notation T, right? So T is defined. So T was originally defined from omega to omega. Another question I ask, right, is can we define an analogous transformation that I'm still going to call T, that is defined from X to X? Okay, so how can we do that? Well, if you think about it, there's not so many choices, right? So you would take the input X, right? And I need to define a transformation of X. So a T of X would be another function that goes from omega to R, right? Assuming that I have here just a single channel. So it means that I need to take a pixel, and now I need to map it somewhere. So there's not much you can do, right? I mean, the natural way to think about it is just to define a transformation that is just acting inside, right? And this T minus 1 instead of T is just a convenience, right? Because if you think about moving an image to the right, right? If you want an image to the right, you need to change the origin, right? By moving it to the right, to the left, right? So that's why we have this inversion. Right, so this is what's called, in technical terms, this is called like a linear representation. Okay, and I think that maybe Sebastián last Tuesday told you a little bit about, hinted a little bit about this connection, because obviously, as you might suspect, when I have different symmetries or transformations, I can compose them, right? There's an algebraic structure in the space of transformations that has actually what's called a group structure. Okay, so I have a group that is acting on this domain, right, like this omega, and then when I see how this group is acting on X, right, so if I transfer the action of the group from the domain omega to the signals on omega, in technical terms, what I'm doing is something that's called a group representation, right? I'm finding a way to represent transformations on elements of the group as linear operators over some space, right? Because what is a key property here, right? A key fact. Let me just maybe write it like this, okay? Just to avoid confusion, right? Like a key property is that T is a linear operator. Okay, you can verify that this operator is linear. Okay, so in other words, T of alpha x plus beta y is equal to alpha times T tilde of x plus beta times T tilde. Okay, and this of course doesn't make, it's not even defined in the space of the domain, right? So I have a linear operator when I lift it to signals, but not when I have not when I have transformations of the domain, right? Because the domain might not even be a vector space. All right. Okay. Any questions so far? No? Okay, perfect. Okay, so there's actually many many motivations, many reasons why we might be interested in symmetries. Some of the motivation, right? Or like why should we care about symmetries? Maybe you can even think that you can look at physics, right? Like from physics, there's a very powerful connection, right, between symmetries and something else. So let's see if someone can infer, like in physics, every time I have a symmetry, right? Like for example, I know that the laws of mechanics might be invariant to changes on the on the point of view, right, on the choice of reference frame that are just affine, like just a translation of the reference frame, right? So it doesn't matter where I put the origin, right? So the symmetry gives rise to something in physics that is powerful and is in a sense like what gives us the language to describe the laws of physics, which are conservation laws, right? And there was the work that really formalized this connection, and if someone here is familiar, it's called the Noether theorem. Which I think gives it like a very powerful vision on why we care about symmetries, right? So like every time I have a symmetry, I know that there's something that is conserved, like a conserved quantity, right? And this is really something that we can use to somehow simplify or like make progress and really identify the key physical property, like the behavior of physical system. Okay, there's another, if you think about like instances where symmetries have been useful to make progress, another famous example from, let's say, math, right? Mathematics. We can look at Galois theory, right? So Galois theory was really trying to understand the structure of solution, like polynomial solution, like solutions of certain polynomial equations, right? And as you remember, maybe you might heard the story, right? There was people were like, there was like a roadblock, okay, quadratic equations, there was a solution, quadratic equation solution by some Italian, and then there was like a increasingly complicated to come up with these solutions for higher degrees. So the approach of Galois was maybe instead of trying to understand this solution itself, I might want to first try to understand the symmetries of the space of solution, right? So what are the changes I can make into the polynomial, and how these changes in the coefficient of the polynomial might affect the changes in the structure of its roots, right? And so this is how he came up with basically breaking and solving the problem, right? Basically, in the last theory, you basically understand the polynomial roots by first studying its invariant structure. So of course, we are not going to pretend that we can, reach the same level of, beauty or like, impact as these two applications, of course, but somehow that's the spirit, right? That we want to really try to make progress, like understand how we can learn these very complicated functions, perhaps by first understanding well their symmetry structure, right? And the whole point is that the symmetry structure in many applications is actually something that is known from the physics, right? That we can use it as a strong way to regularize the problem. Okay, and so there's a bunch of questions that you might ask, right? Is that how much you expect to gain with sample complexity? Symmetries. There's other questions, right? How to define algorithms, or like algorithms or architectures with prescribed symmetry structure. And of course, like a related question is that is symmetry sufficient, right? So are we going to be able to correct the problem by just understanding like symmetries? So there is of course there are reasons to be skeptical, right? And the first reason maybe to be skeptical is that let's first try to make things a bit concrete, and let's focus on, let's say, image classification, right? So your goal is to to learn functions that relate to the presence of certain object, right? And so that's the function that you're asked to learn. And so you might start by saying, okay, what are the symmetries that I know that this function contains, right? So you might agree that if you look at, I don't know, if your goal is to recognize, I don't know, to recognize some object, maybe like a face, like a person. So let's start. I mean, what are the symmetries of the domain that we would maybe all agree here that this function is invariant against? Right? So maybe you can take the domain, right? And take a position of the pixel and replace it by some affine transformation. So what is this thing doing? This is actually what's called a rigid motion. And I don't know if maybe this is a group that you studied last Tuesday with Sebastian. Okay, so what this is doing is basically taking the domain, taking this person, and just putting it right, just basically applying a change of variables that is like an affine transformation, right? So it's maybe just moving the thing and then rotating the thing and maybe making it bigger or smaller. But we all agree that these transformations do not change the question whether there's someone in the image or not. Okay, so this is a group, and these of course these form a group by composition. So we might be very happy that we have now a very large family of symmetries, right? We have a symmetry with respect to any rigid motion. So the question, let's call here, let's assume that here is just part, right? We are just looking at the spatial symmetries. So how many degrees of freedom have we gained, right? So in other words, we started with a very complicated learning problem where the input was in a very high dimensional space. Now I'm telling you, oh, but wait a minute. You don't need to learn you don't need to learn a generic function. Instead, it's sufficient to learn a function that is just invariant with respect to this rigid motion. So how much did you gain? Asking the question here for the audience. Anyone? How many degrees of freedom we have here in this group? Okay, maybe people are. Do we have? I don't know. Do we have something?
So you have an angle, you have a scale, no, and a translation.
Good. So you can look here. Good. So A is a 2x2 matrix, right? And B, because this is in R2, this is just a two-dimensional vector, right? So even if you are a little bit sloppy, right, and you don't, but you see that you count how many parameters you have, that is parameters in the transformation. You have 6 parameters, right? 4 in the matrix and 2 in the vector. So what it means, just think about geometrically, right? So this is your space. Let's call it imagine that this is the space of images, right? This is the domain where your learning is happening. You have an image here, right? The way you can think about symmetric learning is that now instead of your inputs being points, which are kind of images, now your inputs are what we call orbits, which is an image alongside all the possible transformations of the image, right? So this is the orbit, which is the ensemble of all T of X, where T belongs to the group, right? Like a transformation. So here the point is that what is the dimensionality of this orbit? Right, in this example, it's a 6-dimensional object, right? Because I can move around this orbit by transforming X. So how many ways? What are the possible ways I can move? Is how many ways I can parameterize a transformation, right? In that case, it just has 6 ways. right? So in this example, only 6 dimensions in the orbit. Okay, so because this space had a very large dimension, right, like dimension D, I'm killing 6 dimensions, right? So do you think we have gained a lot in terms of breaking the curse of dimensionality?
Doesn't seem like it.
Doesn't seem like it, right? You are going from D, that is 1,000,000, to maybe 1,000,000 minus 6. Not great, right? Of course, you can think about, like another extreme, right? This is an extreme example where the group is very small, right? The group only has 6 parameters. Now we have another example. So this would be kind of example 1. That is the rigid motion. And now we can think about an example 2, which is, let's say, a permutation, like a set, set invariance. Okay, so now here your input domain would be just a set of elements, right? So this would be just x1 to xl, right? And the transformations go from omega to omega is just to take any element xi, right? Sorry for the notation. That would be, I have elements, I have nodes, let's say node 1, 2, to node L. And the transformation can be to map it here to any other, like a T of I, right? That is invertible, right? So this is actually a permutation. Okay, so visually, I have a bunch of points, right? And the only thing that these objects, their order is irrelevant, right? The only thing that matters is the collection of measurements I have on those things, right? But the order doesn't matter. So in that case, how large are the symmetries? Okay. So how many? How many symmetries here? What is the size of the group? If the input here, the number of pixels, so just to be consistent, the number of pixels would be D, right? So how many permutations I have? So G, right, is the size of the permutation group. Yes, it's a D factorial, right? In that case, which is much, much larger, right, than the previous example, right, where I had just killed, 1 degree of freedom, right? So if I have here in the previous example, right, if I have a grid of D pixels, and I think about how many translations do I have number of translations that is equal to the number of pixels, right? In this other example, the number of pixels I have, like the number of transformations I have, is actually D factorial, right? So this is actually much larger than D to the basically D that I had before. Okay, so here you might ask that like when the group is very large, symmetries might become an important, might give you like a big boost, right? Because they give you like a prior that is an inductive bias that is very strong. When the symmetry groups are very small, the question is not so clear. Okay, and I'm just going to make a plug here, like a pointer, is that to know more, or like for further, about gains in sample complexity as a function of the symmetry group. You can check on the sample complexity of learning under invariance and geometric stability by Roberto Vietti, Turi, and myself. That is in this year's. Okay, I'm not going to go into the technical details of this work, but if you are interested in this, like how the size of the group changes sample complexity, you can check this page. Okay, very good. Any questions so far? No? Okay. Okay, so I'm gonna continue now for a few minutes, and then we are gonna take a break. So let me something that I maybe didn't formalize, but I think it was pretty clear from the exposition. That is the definition of the group, right? So basically, just the fact set of symmetries form a group by composition. Okay, and so what is it? Let's just recall. I guess that's something that you saw on Tuesday, right? So what is a group, right? So a group is a set of objects that come with some operation, so have some special properties. So remember that there's like an existence of identity. That E times X equals to X times E equals X for all X in the group. And then you have the group is closed by this operation. And then you have also the existence of an inverse, right? So like for every X in the group, there exists inverse such that X times X minus 1 is equal to identity. Okay, just that this is just a little reminder that we might be using today. Okay, and also let me just say that this operation is not commutative. Okay, this operation is in general not commutative. Okay. Perfect. So maybe that's now it's a good time to take a 2-minute break. I'm gonna take a 2-minute break, and then I'll be back. Let's say in 3 minutes. At in your time would be 5 p.m. And then we are gonna continue for 1 more hour. Okay, so let's resume. Okay, now let's continue. So let's just now describe the simple concept of invariant and equivariant representation. Okay, so what we're going to say is like we are going to describe, we are going to, in order to learn functions that have these that are aware to the symmetries, we are going to construct. So we are going to be interested to study approximation spaces that we are going to study approximation spaces that from similar representations of the form mapping that takes our input space and map it to another space, right? That's what we call this feature space. Okay, so this, and then once we have this representation, we can use it to define an approximation space, right? So then, or hypothesis space is then a linear map over, right? So basically now F can contain functions that are of the form some linear operation times phi of x. Okay, let's here's for the operation. Okay, so this is a very popular, it's a very natural way to think about a way to construct hypothesis space. And now, of course, how can we make this hypothesis space aware of the symmetries? Well, by asking the relevant property for the representation. Okay, and so a representation phi from the input space to the representation space is invariant to a certain group of transformation G if that's the obvious definition, right? Is that for every x and for every transformation in my group, we have that the representation of T of x is equal to phi of x. That's probably something that is obvious for everyone. And then there's the analogous property for equivalence, right? So like a representation is let me just assume that G admits a linear representation over, right? So basically the group is not just acting over the input, but is also acting over the feature space. Okay, so then our representation phi is equivalent to G if it commutes with any T on G. What does it mean? It means that for every x, the input, transformation, if I apply first the transformation and then the representation, I get the representation that is acting over phi of x. Okay, So remember that. So this remember our previous notation, right? That whenever we had a transformation that is acting on something else, we put like a tilde, right? So think about this as some kind of tilde, unless this could be like a different tilde, right? Just to illustrate that the way this transformation is acting on the feature space might be specific. But the key point is that we have this commutation, right? Like for a given t, we have an exact correspondence on how a given element of the group is acting on the objects in both X and Z. All right. And I guess that just to make sure that we agree and we are comfortable with what these two notions mean, let's just look at a very simple example. So I'm going to consider, let's say, signals that are integrable, like L1, right? So I take a function in R that is integrable, and I consider as a representation just integrating X. Okay, so just like the sum of the function. So is phi invariant to translation? Okay, so let's verify that. So of course we define the translation, so we can just define it with some parameter tau. Okay, so we described it before. Sorry, it was like this t, like a transformation. Translation is a transformation that is indexed by some parameter tau, right, of X, that then is acting over pixels by just shift, right? If you remember, right? So tau here is just the parameter. So now if we compute phi of tau of X, we apply the definition, and it's just tau du, right? And by change of variables, this is obviously the same as the integral of x of u du, which is phi of x, right? Is now let me just make sure that we understand. So like is phi invariant to like dilations, which is another group. So what is a dilation? Would be just like a t of s of x, u, that would be just maybe x of s times u. So is it true that the representation is invariant to dilation? Yes, no?
No, after the change of variables, you have an 1 over s, no?
Yes. Okay, so that's no. Okay, so it's not true that phi of s of x, that's not true that it's phi of x. Indeed, right? There's a change, there's a scale in the change of variables that makes this not invariant. And you can actually see, right? If you take an image, a signal, and you shrink it, right? You can turn it into a zero, right? Okay. Now let's think about another example where we kept again consider an integrable function, and then just assume that it has like complex support. Yeah. Now I'm gonna define a representation which does the following. It's u times x of u divided by x of u. Okay, so what is this representation doing? Anyone who can see what this is about? this is basically finding the center of mass, right? So this is just you have a signal, right? And I'm just gonna decide. It's a strange center of mass because I'm just not taking the absolute value, but that doesn't really matter, right? I could just take it. Okay. So is what is interesting, right, is that the difference here is that in this example, I asked the question, so is phi tilde equivariant to translations? So let's try. Let's verify this, right? So phi tilde of some translation of x. This is just the integral of u times x of u minus tau du. And remember that the denominator is something that we already found before, right? That is just the integral of x of u minus tau, right? So this is the same as u plus tau times x of u by applying the change variables divided by x of u du. And so if you decompose the numerator, you can already see that you get phi tilde of x plus tau. Okay. So the action of the group, like translating the input and applying the representation, is the same as first applying the representation and then applying the translation, right? Like so the two operations, right? You have some x, you can map it to your representation, or you can apply some transformation t. So this diagram commutes, right? Here you have x, now you can apply the representation t. And here you have x. So this is the commutative diagram. All right. Okay, so now these are just like a very constructive examples, right? Like very, examples that I built by hand. One question that you may ask is there something a bit systematic? Is there a systematic way to construct invariant representations? Right? So is there invariant or equivariant representations? So here we might just to illustrate a little bit this question, we are going to focus on a particular class of transformations that are generated by what we call a one-parameter group. Okay, so like a definition. Here's the one parameter. So let X be a Hilbert space. This is actually, for example, think about X, as I said before, as the space of signals that are defined over some domain, right? Like, for example, L2 of some domain. One parameter unitary group. It's a family of operators that are indexed by some one parameter. This is basically the time. From x with t that is in R, such that we have certain few properties. We know that for all t s that are in R, we have the group structure. So phi of t plus s is equal to phi of s times phi of t. Then there's a little bit of smoothness, right? So like basically the lim s goes to t of the difference between these two operators is 0 in the operator norm, right? So it means that as you have, as the two parameters get closer to each other, the two operators converge to each other in the right sense. And then the third property is the fact that it's unitary. It doesn't change the energy of the function, right? Like phi t of x is equal to x for all t. Okay. So in particular, this group is abelian. So remember, like an abelian group is a group that commutes, right? And so I guess that you all see why this is true, because I can look at phi of s and phi of t and apply property 1, which is phi of s plus t. But this is obviously the same as s phi of t plus s, right, by definition, which is equal to phi of t, right? So this is the obviously commutative. And so if you think for now, like if you remove the kind of the jargon and the kind of the mathematical things, at the end of the day, I'm telling you. Here's a bunch of like an operator, right? If you think about an operator in a Hilbert space, you have to think about kind of a very large matrix, right? It's a thinking, if you want to visualize it, think about the matrix. So I have a bunch of matrices, but they are indexed by some parameter t, and these matrices commute with each other, and they're unitary. So if you have a family of matrices that commute with each other, and they are unitary, what is the kind of structure that you might suspect that is going to emerge? So if you think for a second, you will find that this result is not extraordinarily surprising, right? So this is a theorem from Stone, from actually the 30s. It's an old result that basically gives us like a, the characterization that you should expect that works for finite dimensions also works for general dimensions, right? So basically what it means is that there's a correspondence, a one-to-one correspondence between self-adjoint operators on the space and one parameter groups. It's a one-to-one correspondence, one parameter, unitary. So what does it mean? Just to try to make it a bit more concrete, right? So in particular, given a group of this form, there exists A that is self-adjoint, so it means that's symmetric. Such that for all t, I can express this matrix, like this operator, using functional calculus. Right? So I can just think it as the complex exponential of some adjoint operator. Okay, so this is like a matrix exponential Okay, so what it means is basically if you take the complex exponential of a symmetric matrix, it means that the way this operator acts on vectors, you take the vectors, you decompose it into the eigenbasis, and then you apply this function, in that case, this complex exponential, to each of the entries, right, of the decomposition, right? Okay, so now let's try to unpack and to understand what this means, right? So A, in that case, is called the infinitesimal generator of the group. Because if I know A, this self-adjoint operator A, then I can basically generate all the possible copies, right? And there's many interesting connections and properties that we can extract from this. For example, if you think about like the kind of the tangent space, right? If you think about this one parameter group as some kind of like a manifold, right? Like the tangent space, which is something that is called like a Lie algebra, is indeed, you can see that if you take the derivative of this equation with respect to t, and you set t equals to 0, you will see that the derivative is precisely A, right? Is a general point. So now let's try to go for exactly what we care about. So what does it mean? It means like a self-adjoint. What does it mean? It means precisely what I want, right? Is that there exists an eigenbasis, right? The basis of L2 of X of this Hilbert space A of Vk equals lambda k Vk. Okay. So these are the eigenvalues. So when I have this property, right, I know that by definition then, if I think about how the group is acting, right, on each of these eigenvectors, by just applying the definition of the functional calculus, I know that this is going to be e to the I t lambda k times vk. Right? So basically, vk are eigenvectors of group action for all t. Okay? And this, again, should not be surprising, right? If I have a family of operators that commute, they share the same eigenstructure, right? So that's what this eigenstructure is, precisely the one that is prescribed by this infinitesimal generator of the group. So, and then I don't know if Celestia made this connection, right? But this is like this basis, right? That is V that corresponds to this basis is it's similar, or it's like it's interpreted as the Fourier basis. Okay. So, and just to make sure that people are comfortable with that, is that now let's see how the group is acting on the inputs, right? So basically, now I have for any given input x, how does the group act on x? So what is this? So any ideas? What should I do first? If I want to understand how this group is acting on an input x. I don't know if the question is clear. So how do you, if I know what the group is doing to each of the eigenvectors, how can I now use this information to see how the group is acting on arbitrary inputs? Well, I need to use the group is like the group is defining a linear representation, right? So it's like a, so I need to use linearity here. So X, I can write it, I can decompose it in my eigenbasis, right, with certain coefficients. And now I can simply say that the group acting on X is the sum, okay, of alpha k, the group acting on each of the eigenvectors. Now I can apply the definition, right? I can apply what I just got before. Alpha k times a to the I of t lambda k times. Okay. So why is this interesting for us? So now the question I get for you is, say I want to build an invariant representation to the group. Does this Stone theorem help me in this problem? How can I use this Stone theorem to build an invariant representation to this group of transformations? Any ideas? Okay, I might have lost everyone here. Okay, let's go step by step. So let's see. Let me try to visualize exactly what happened. Right. So here, I know that I can take my if I look at what happens, trying to express an input, like an input here in this problem, is equivalent to the coefficients, right, in a certain eigenbasis representation. Okay. So basically, I can always associate X with the collection of all the coefficients in a certain basis, right? I can express, in a Hilbert space, I can just choose any coordinate system I want. So I'm going to choose this coordinate system. So now, what happens when I start to move to transform X according to this group? What is the action that I see? What is the effect that I see at the level of these coefficients? So these coefficients now, alpha k, now becomes what?
The exponential with the eigen values.
Correct. I replace alpha k by alpha k times this complex exponential. Right. So this indeed, because this is all like a basis that is in the complex, right? Like all this theory of self-adjoint operators, as you know, they involve like a self-adjoint is a property that here can have like a bunch of complex numbers, right? So basically, alpha k is complex, right? And so if I can visualize a complex number, I can visualize it like maybe like a vector into D, right? If you want. So what is the effect of the group acting on my coefficient? If we want to visualize this thing. So what happens if I take a complex number and I multiply it by a imaginary exponential?
You're performing a rotation in this to
Yes.
the representation.
Thank you very much. Okay, so it's basically just moving this thing around, right? So that when I apply this direction of the group, this coefficient is just moving around, and it's moving with the speed that is determined by this eigenvector, by this eigenvalue. So, what do you think? How would you construct an invariant? So, like a quantity that does not change as you apply the group operation. So, what is a property that would be preserved for any point in that circle?
The modulus.
Yes, very good. Okay, so here's a candidate for representation. I could just decide to keep, right, the collection of all the modulus of basically the dot product between x and k, right, for all k. And we can indeed, so it's like a easy fact, is that phi of the transformation of x, right, is equal to phi of x for all x and for all t, right? Just because the modulus of alpha k times e to the I t lambda k is equal to the modulus of alpha k, right? Just rotating in the complex plane doesn't change the modulus. Okay? And so there's an interesting, so there's a bunch of interesting things, right? Is that here we have built an invariant representation that contains a linear. So basically we go from x, we transform it to this coefficient, right? So like, because it's the basis, we just perform a linear transform that is multiplying by v, right? To extract these alphas. And then from the alphas, we apply the absolute value, like the complex modulus. So we have an example of a shallow architecture, right? So this is basically a shallow architecture that generates a G invariant presentation. Right, and to give an example from that class, right, just an example, let's take that phi t of t, so phi t of x, u is just applying the translation. Because with the translations, you can verify that they are, they define this one parameter group that is unitary. And so in that case, you can verify that the family, like the self-adjoint operator, diagonalizes in the Fourier basis. Right? So in that case, alpha k, right, is the product between x and the eigenvector vk is precisely the Fourier transform at frequency, let's say frequency k, right? And I'm not sure if Sebastián covered a little bit harmonic analysis. Anyway, that's just if you don't know, if you're not very familiar with Fourier transforms, for today it doesn't really matter. For next lecture, we are going to use it a little bit more, but for now, just you know, we just need to observe that this construction that we had done before, in the case of translation, becomes something quite concrete. And so, in other words, the representation that we have just obtained before is just the absolute, like the complex modulus of the Fourier transform of the signal. Okay, so this is the complex. So indeed, it's very from the properties of Fourier transforms. You know that if you take a signal and you translate it, you get the same, like the Fourier coefficients only changing their phase in the complex phase, right? So if you kill the phase, you just keep the modulus. The modulus of the Fourier transform doesn't change, right? So you get translation. But in fact, it's are we done? I mean, is it something that you would want to use or implement in practice, right? So in fact, it turns out that there's a bunch of shortcomings about this construction, right? So in a sense, we have discussed about the strategy that is not a good strategy, but just the purpose is to, understand why it's not a good strategy. Okay, so there's a bunch of shortcomings. Of this axiomatic of this construction. So there's a bunch of them. So here, one shortcoming is that, yes, this representation is translation invariant, like in the sense invariant to the action of the group. But the problem is that invariants, or like symmetries, are essentially a very rare, very brittle notion. And again, think about real life, right? You are seeing things in your, with your eyes, and yeah, if you move your head, right, you might see objects that seem like that are translating in front of you. But is it a real translation? Well, things are never really going to be like an exact translation, right? Just because you can actually see that because everything is in 3D as we project it to the 2D plane. As soon as there's a little bit of a like out of plane change, things are not exactly translation. Okay, so the way you should think about it, right, is that we have a kind of the space of all possible transformations that we could do to an image. So basically, these are all the transformations, right? Everything that can map one image to the other. And then somehow, the group of translations is a very small group, right? So think picture is not so good. Maybe just think about like a group of translations here, right? So this is the identity, and this is just like a group of translations. And in fact, this larger group here, right, like that group of translations, is a subgroup of something much larger, right? So these are basically it's called like the automorphism. Right, so basically, these are all the possible transformations I can make from the domain, like in the case the grid, to the grid. Right, so basically, I can just change any pixel. I can map it to any other pixel. Right. So before, remember that we described like this rigid motion, this mapping was affine, right? It was just 6 parameters that was defining this T of U that was like a affine transformation. But now if you make any possible transformation that is invertible, that's what's called a diffeomorphism, right? So these are diffeomorphisms. Okay, so the group of possible diffeomorphisms is much, much, much larger than the group of translations. Okay, so we convinced ourselves that along these transformations here, we have kind of exact invariance, right? But the question is that what do you think, or do we have any information about what would happen outside? Well, of course, if I take maybe a random point, like a diffeomorphism that is arbitrarily chosen, a diffeomorphism can be very nasty, right? It can completely destroy the context of an image. But it turns out that there's a, like a certain family of diffeomorphisms that are, so these are basically diffeomorphisms that are near translations. Again, we are going to formalize this thing next week, right? So if there are structures that are almost like a translation, would you expect your invariant criterion to completely break out? Well, I don't think so, right? I mean, if the same way that we suspect that the function we need to learn is invariant to translations, we suspect that if you have a transformation that is almost a translation, the function cannot change too much, right, along that direction. And so somehow what we see is that our notion of group invariance shouldn't be like rigid, right? So when we build invariant representations, we should not only worry about, okay, does it respect the axiom of being invariant, but we should also see what happens nearby this group, right? Whether it's stable to things that are almost a transformation, almost a symmetry, right? So basically this is like a stability to near symmetries, right? That's the key. That's the key property, right? That somehow this axiomatic representation that I described is not going to be great at, right? And again, maybe for today, there's no more time. As I said before, as I said at the beginning, I need to leave a little bit earlier today, so we're going to discuss this next time. And there's another shortcoming. So basically, that this representation that we just built might not be optimum. That is, now let's think in the grand scheme of like in a bit more like high level, right? So we want to build representations to learn interesting functions, and these representations should incorporate the symmetries. But aren't we forgetting something? What is the other property that a single representation should satisfy? And maybe I can just motivate a bit better this question by writing you down like an example of a representation, and you tell me if it's a good choice or not, right? So what if I choose phi of x to be always 0, right? That's my representation. Is this representation invariant?
Yes.
Is it stable?
Yes.
Right? Very stable. So, but is it a good representation?
No.
No, right? So what is the kind of the property that we need to use to balance against stability? Right? So obviously, we want to balance stability or invariance with what we call a kind of expressiveness, right? In other words, can this representation express all the functions that are symmetric still, right? So basically what I mean is that can, or hypothesis space that is f, that is f of x, tau phi of x, approximate any or like a large families of invariant functions. Okay, so that's the other piece of the puzzle that we should not forget. And so now we can go back to our example, like back to our this modulus of the Fourier transform. You might ask, okay, is this representation good in the sense that it's able to discriminate, right? To express, like to distinguish between different examples. So in other words, is it keeping the information, as much information as it could? And so the answer, and I guess, I don't know if you have seen these pictures, is that the answer is clearly no, right? So is phi discriminative? And the answer is no, right? There's many examples. So many examples of x that is x and y with very different very different properties, yet phi of x equals phi of x. Right, and this is because in the Fourier domain, the phase, like the phase of the Fourier coefficients, is actually carrying a lot of information. Right, with the phase you can actually reconstruct it. Right, there's some examples, right, where you can actually reconstruct the input almost essentially with the phase. Right, so you are throwing the phase information, and so basically just as a conclusion here for today, right, like a conclusion so far. From today is that basically invariant representations built, I'm going to write it like this, too quickly, in the sense that we just use the shallow network to build them, suffer from lack of stability to near symmetries and lack of expressiveness due to like basically killing Fourier phase. And so actually next lecture we're going to see how to mitigate this, right? So next lecture is how to do much better with Webley-based representations instead of Fourier-based. Okay, so next lecture we are going to formalize this notion of near translation. We are going to do it on the grid by introducing the formations, and we're going to see how we can resolve these two shortcomings with like a very axiomatic construction that will lead us very naturally to CNNs, to convolutional neural networks, right? Like with representations, and this is going to lead to the CNN. Right? This is what is going on. Okay. So I'm going to stop here for today. Maybe you have time for a couple of minutes for questions if someone has. Otherwise, of course, I'll send you the slide, like the materials, and then I'll see you next week. Okay. Okay. Perfect. So then, without I'm just gonna stop this. Stop sharing. And I guess I'll see you next Thursday. Bye, everyone.